Today my 7th hour is sneaking out after my 3rd hour got this lesson. So this video will be made just primarily for that 7th hour that's not going to be here. Independent and dependent events. We just got done with discussing some basic probability, some theoretical probability, experimental probability. Now we're going to take on multiple events, and we got to determine first off whether they're going to be independent or dependent. If they're independent, then the occurrence of one event does not affect the occurrence of the other event. They stay totally away from each other. And so there's a couple ways you might see this written. It's going to be the probability of A happening and B happening. Another way we write this is the probability of A and B. We use this intersection symbol. My next video will kind of explain that more. But to figure this out, since they're independent, I just simply need to do the probability of A times the probability of B happening. Since they don't have any weight on each other, I can just multiply them. They each can be a factor and just multiply them together. And that would be my answer. Let's kind of play with it though to determine whether or not they are going to be independent though. Let's take this student is taking a quiz and randomly guesses the answers to 4 true-false questions. Determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. So the question is, the probability of getting 1 and 2 correct, are they independent? Well, if I'm looking at it, suppose that I get question 1 correct. I might not know it's correct during the test, but I got question 1 correct, and now I'm going to question 2. Whenever I randomly guess on question 2, does the fact that I got question 1 correct have any weight on whether I get question 2 correct? No. So are they going to be independent events? Yes. I can just simply take the probability that I get question 1 right times the probability I get question 2 right, and that will tell me the probability of me getting question 1 and 2 right. So probability I get question 1 right is 50%, is true false. All right. The probability I get question 2 right is 50%. So my answer would be 1/4. Okay, let's look at one that's not going to be. I'll go ahead and spill the beans on it. This one's not going to be. Let's see why. So I have 4 students, 1 boy, 3 girls. And the teacher is going to randomly select one of the students to be the speaker and then a different student to be the recorder. Determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. Kind of sounds like they would be. They're set up the same way as the last example. I'm wanting to get the probability of girl and let's look at this. The probability that I select a girl first, well, there was 3 girls out of the 4 students. Okay. Now the probability I select a girl second, well, it has to be a different student. So now that I've taken that girl out of the sample space, there's only 3 people in there. And so I get 2 out of 3. These numbers don't match. Whenever my sample space is being affected like that, that's a big red flag that I now have dependent events. And whenever I have dependent events, I'm going to need to very slightly tweak my formula. We'll come back to that one. If you want to not erase it, we'll come back and finish it. So 2 events are going to be dependent when the occurrence of one event does affect the occurrence on the other event. So this brings in this whole idea of conditional probability that me and 3rd hour got in a huge argument about. I'm going to spare you the argument, but I might include a video that you can watch that will describe my side of the argument. But it brings in conditional probability. And conditional probability just means that whenever I'm finding the probability of event B happening, I have to take into account the fact that A has already occurred. I'm not going to give you a formula for it just yet, but this is how we write it. Probability of B given A. So this line right here, I would say given that A has already occurred. So I need to revise my probability of A and B for dependent events. Okay, luckily I am still using multiplication and I'm still finding the probability of A to start off with, because the probability the first event occurred is going to be just independent of anything else because nothing else has happened before it. But now I've got to take the probability of B given that A has already occurred. So whenever I did my probability of girl and girl for the speaker and recorder on example 2, I got to take the probability of G. I really should have done like some different variables, but I think I'll manage. And I got to multiply that by the probability of choosing a girl again, given that I chose a girl the first time. So just regular probability that I chose a girl, as stated earlier, was 3 out of 4. Now, taking into account that I've already drawn a girl, probability of me getting a girl the second time, well, there was 2 girls left in the pool out of the 3 students. So that gives me 6 out of 12. This teacher had a 50% chance, 1 in 2 chance of selecting 2 girls out of the 4 students to be the secretary and the recorder. Okay, let's just look at some examples and let's try to determine whether or not we're going to be independent or dependent. And then I'll determine how we need to attack it. So as part of a board game, you need to spin a spinner. And it's divided into equal parts. I want to know the probability of getting a 5 and getting a number greater than 3. Probability of getting a 5. Oops. And something greater than 3. So let's think about this. Is this independent or dependent? It should be independent. If I spin a 5 on this first one and I get the spinner to land at 5, it really shouldn't have any effect on what I'm going to spin the second time. So we have independent events. I'm going to hit pause on the video. You work this problem out while I work it out, and then hit play, and then we'll see if our answers match. We're not looking too likely on this. 5 in 64 chance that I roll a 5 and then a number greater than 3. Okay. If you want to decimal that out, you're more than welcome to decimal that out. I think it's like less than a 1% chance, 0.078. I guess it's not less than 1% chance, between a 7 and 8% chance, 7.8% chance that happens. All right, this next one's going to be where if you were, I'm getting my examples wrong. All right, so let's suppose you go to your rich friend's house, and your rich friend has this big basket of money, and there's $21 bills in there, and then there's 5 $100 bills in there. And he's saying, okay, everybody line up, and you're first in line right there. And he says your name, we'll call you John. You get to draw 2 bills out of here. Well, I'm really hoping I get the 2, both of my draws are the $100 bills. What's the probability that I draw a $100 bill on both of those first draws? All right, let's take a look at it. I want to know the probability of a 100 and a 100. Now, first of all, we got to determine, are these going to be independent or dependent events? All right, these are going to be dependent events because when I stick my hand into that basket on the first draw, the probability of me drawing a $100 bill, there's 5 $100 bills in there. Out of the 25 bills. Okay. However, so I take that $100 bill that I got right, I stick it in my pocket, and now I want to know the probability that I reach my hand in there again and get another $100 bill. Well, now there's 4 $100 bills in there, and there's only 24 bills. So multiplying this out, oh, I could reduce both those. That might help. 1/5 times 1/6, 1 in 30 shot that I get 2 of those 5 $100 bills. If we're going to decimal that out, you can call it 0.03. I think it's repeating, or just like 3.3% chance that I get 2 $100 bills. If you ever play with playing cards, all this kind of works into the probability of you getting cards. I'm not teaching counting cards here. Third hour is a little worried with that. This is not how to count cards. That's a different lesson that I usually don't teach. So let's look at this. So when we have playing cards, we have 52. A standard deck's going to be 52 playing cards. And of those 52 cards, they're going to be split up into 4 suits. There's going to be hearts, clubs, diamonds, and spades. So that means that there's going to be 13 hearts, 13 spades, 13 of each of those suits. And each of those suits are numbered 1, which is ace, all the way up through 10, with a jack, a queen, and a king, giving you 13 cards. This is where if you were here, I would have playing cards in my hand. I had them on the desk ready, but obviously you guys aren't here. So let's try part A right here. I am selecting 3 cards from this deck, and I want to know the probability I get all 3 cards to be a heart. You know what that means? That means the probability of me getting a heart, and then drawing a heart, and then drawing a B. Came from a heart. So probability of me drawing 3 hearts. Okay, so let's just go back to sticking our hand into that deck. Whenever I stick my hand into that deck, there is, let's see, 1 out of every 4 cards is a heart. So you can think of it as it's going to be 13 out of 52. 13 of the 52 cards are going to be a heart, or that reduces down to just 1/4. 1 out of every 4 cards is going to be a heart. Now, this has something called with replacement. So I pull that heart out of the deck, and then I'm going to slide that heart back into the deck. I'm going to pull again. Well, if I put that card back in the deck, there's still 52 cards in there. And of those 52 cards, 13 of them are hearts. And I do that again. I have a 1 in 4 chance on each draw to draw a heart, which gives me 1/64, which is some decimal. It seems like I already did that, like 1.6%. Not very likely to draw 3 hearts. 1.6%. Well, so that was independent. Look at part B. I'm not replacing the heart. Suddenly, when I don't replace the heart, my sample space is going to change. So we're going to hit pause again on the video. I'm going to work it while you work it and see if you can work it with that sample space changing and what's going to happen to my percentage. We'll see if it goes up or down. The probability changed a little bit, not much. Went from 1.6% down to 1.3%. Look at these denominators down here. Each time I drew out a card, I didn't put it back, so the number of total cards went down, and each time I drew a heart, the number of hearts went down. So all right, let's get some probability from some frequency tables. So we have 100 random DHS athletes. Asked them if they were left or right-handed. That's what I found. I found that 40 of the ask 100. Yeah, I asked 52 male athletes. Of the 52, 43 were right-handed. I asked 48 female athletes. Of those 48, 44 were right-handed. So I want to find the probability that a male athlete is left-handed. Kind of getting into some conditional probability here. Right? I'm wanting to find the probability that a male athlete is left-handed. So I want the probability of a lefty given that they were male. Oops, got my lines confused. So my sample space that a male athlete is left-handed, my sample space is going to be all my male athletes that I talked about. So I said that there was 52. Okay. So this down here was the number of male athletes that I had. And then on top, I just want to look at the left-handed ones. So the left-handed male athletes, there were 9 of them. So it would be 9 and 52. There's, see, 3 shouldn't go into 52 because it goes into 51. So on top right here, it was a number of left-handed and male. And so that's how we would go about this. Let's reverse it up a little bit. I'll work it through with you. I won't turn you loose on this one because this is kind of confusing. I want to find the probability that a right-handed athlete is female. So I want to find the probability that I'm drawing a female given that they are left-handed. So the given part that they're left-handed, I need to get, I'm sorry, it definitely says right. Okay. I need to, my sample space is going to be the number of right-handed athletes that I have. That's going to go down here on bottom. Okay. So the number of right-handed athletes I have, it looks like is 87. And on top, just of these right-handed athletes, which ones were also female? Well, that would be the 44. So on top up here, I put the number that were female and right-handed. So that'd be 44 out of 87. That's kind of different. I'm not going to revisit that. I'm just going to hit on it again. I'm not going to change anything. So remember, dependent probability, when I'm doing the probability of A and B, whenever it's dependent, I've got to do the probability of A multiplied by the probability of B given that A has already occurred. Okay. Now I could solve this explicitly for this probability of B given A and be given a formula that we pretty much just used. You know what? I'm going to go ahead and do that. I'm going to divide both sides by the probability of A. Which is the probability of B given A. This is the probability that I just used on the last slide with the left-handed and right-handed athletes, right? Same little formula I have here. So feel free to use either one, the green or the red. What they're going to do is they're going to give you a word problem where you'll have to use it. I'm just going to use the blue. I've had more luck teaching this with the blue because it's less formulas to remember. That's always a good thing. So we have at a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. What's the probability of a student who buys lunch also buys dessert? So I see it's dependent right here. They're not independent. You know, just because there's some students that are getting just lunch and there's some students that are getting lunch and dessert. If it was lunch on one side, dessert on the other, we'd be looking at something different. So I'm going to first change around my variables to the probability of lunch and dessert. You know what? It told me that probability of lunch and dessert. Probability of lunch and dessert, there's only 10% of students that buy lunch and dessert. So this is going to be 10%. Okay. Now, since it's dependent probability, I'm now going to take the probability of someone that gets lunch. Someone that gets lunch, 60% of the students get the lunch. Times, well, all I have left are the students that get dessert given that they also bought a lunch. And that's exactly what I'm looking for in this problem. D line L. All right. And so I could have solved this explicitly. I can right now divide both sides by 0.6. I get 0.10 over 0.60 is my probability of dessert given that they bought a lunch, which would just be 1/6, which would be 16.7%. That one's kind of weird. I will say it does work out a lot that you're just taking your smaller decimal divided by your larger decimal, because remember, a probability has to be a number between 0 and 1, so that's really the only way that would come out. But play with that some. Here's the practice problems. There is a link, and I have worked all of those in Google Classroom. So let me know if you have any questions. Have a good rest of your day, and I'll catch up with you guys later.